Hey guys, I'm making this video to show off this Cyberdeck that I made. This is the first version of it and I plan on improving it in the future, but it's in a pretty functional state right now. The enclosure is a Meja IP67 waterproof case. I didn't want to really drop the money on a Pelican case, but it seems to be sturdy enough for what I plan on doing with it. I have a couple of holes in the case from the antenna bulkhead pass-throughs and fasteners, but those are still good enough to at least be rain resistant. The faceplates are made from ABS plastic. I know the craftsmanship isn't the best, but I did pretty much all of this with just a Dremel, so it's okay for V1. The subframe is made from a mix of PVC and wood that I got from Home Depot, and in the future I'm hoping to get the money to get a nice 3D printer and get all these materials printed so it'll be a much lighter and cleaner look. Also, I know the wire routing may leave something to be desired, but all the cables are really long, and I didn't want to spend the money on $200 for a specific cable length, so right now it's fine, but it's something I plan on also improving on in the future. The brain of this build is a Raspberry Pi 5 with 8 GB of RAM running a quad-core ARM Cortex A76 processor at 2.4 GHz. The Pi also has an NVMe hat with 235 GB drive, plus a 1 TB external SanDisk for media, maps, and other kinds of files that may be necessary for this build. For display and input, I have a Waveshare 10.1 inch touchscreen at 1280 by 800 connected via HDMI, and my primary keyboard is a Logitech K400 Plus wireless, and there's also a backup folding keyboard that lives in the storage compartment. For radios, first I have two Newelec NSDR smart software defined radio receivers. These convert raw RF into digital samples over USB. Each one has a unique serial number burned into it, so the operating system always knows which is which. ADS-B for the 1090 MHz aircraft receiver, and scanner for the wideband receiver that covers 70 MHz all the way up to 1 GHz. Second, the Heltec Wi-Fi LoRa 32V4. This is a mesh radio and ESP32S3 microcontroller paired with a LoRa transceiver on 915 MHz running Mesh-tastic firmware. I've wired a GPS module directly to the Heltec's UART pins. It is mounted behind the faceplate directly below the display and provides messaging capabilities without a cell phone network as well as GPS positioning data. Last is the Alpha AWS 036 ACM. This Wi-Fi dongle acts as a hotspot to connect client devices as well as monitor mode for when I'm trying to identify nearby devices. We will go into much more detail on all three of these systems a little bit later in the video. For power architecture, the SharkGeek 170 is a 24,000 mAh USB power bank. It feeds the powered USB hub and the Waveshare USB Hat-E. The USB hub powers and then passes data for the ADBS antenna, the wideband antenna, the LoRa antenna, and the SanDisk drive. I implemented this powered USB hub when I found that while writing data, the demand from the SanDisk was too high for the Pi. It started freaking out, especially while I was downloading large media files like maps. So I implemented this solution. The UPS houses 4 Samsung lithium cells that are monitored on the Doombox UI as well as the Raspberry Pi itself. The UPS is a primary power to the Pi, and the Pi is booted by an external power button. Field endurance is probably about 8 to 12 hours depending on the load. One thing to keep in mind though is that the radio, SanDisk, and peripherals will be lost when the SharkGeek dies, so operational power is more like 6 hours. So that was a hardware stack that is driving this user interface. Now I'll be talking about the system architecture that makes this UI able to integrate all the hardware on the Cyberdeck. Almost all the features on this interface is available completely offline, hence the name Doombox. The system can be used as a standalone tool on the Cyberdeck, or you can push this data to client devices via the hotspot. Later I'll go into a little more detail on how each of these systems operate, but here's going to be a broad overview of that backend. So this diagram I like to think from left to right while looking at it. The left hand side you're going to have all of your hardware that is then pushing data and signals to the Raspberry Pi, that is processing them and feeding it to the Node-RED middleware, that is then sending all that information to be displayed on the dashboard. And there's a couple ways to view that dashboard. You can view it on the Cyberdeck itself as an ATAC client or as a client on the hotspot. Starting over here at the top, we have ADS-B that's going to be receiving data from aircraft that are transmitting their position, speed, altitude, and call sign on 1090 megahertz. Right below that, we have the LoRa mesh radio that's 915 megahertz, and that is our Mesh-tastic protocol, the encrypted long-range radio network that connects this box all over the city. And connected to that Mesh-tastic Heltec V4 device, we have the GPS module on its UART pin, and that is sending GPS data through that Mesh-tastic bridge as well. And then we have the RF scanner at 70 to 1000 megahertz. That is going to be our second software-defined radio, and it's going to be picking up things like aviation, weather, amateur repeaters, and business bands. And then we have our alpha adapter for Wi-Fi, and that is creating the access point that the team or devices can connect to, and that is going to be pushing this tactical dashboard over to external client devices. And then we have our internet, and that is not mandatory for this build, but it will be fetching things like real-time crime data, local and national news, significant weather events, and also our POI data for the map filters. And you can filter things like bridges, electricity, hospitals, things like that. Alright, we'll come over here and look at the Raspberry Pi and what it's doing with the information that's being fed by the hardware. At the very top, we've got dump 1090 FA that is taking the ADS-B data and using FlightAware's open source decoder to take the raw RF and produce structured aircraft data on a local TCP port. And here, the LoRa mesh and GPS both feed into this Mesh-tastic bridge. This makes it to where the Mesh-tastic is the exclusive owner of the serial port. Nothing else is allowed to touch this port because the Mesh-tastic protocol is a binary protobuf over serial. If two processes are reading the same serial stream, they'll interleave bytes and the parser fails. The bridge takes every packet, position, messages, and telemetry and routes it appropriately. And then the RF scanner feeds into the radio supervisor, which handles tuning, scanning, and coding the audio as Opus and streaming it over HTTP. And then for the alpha adapter, this is managed by host APD and DNS mask. That's the access point daemon and the DHCP server. That's what hands out IP addresses to everyone who connects to the hotspot. And then the UPS hat feeds the UPS monitor service through 12C. That's how we get the per cell battery voltages, state of charge, current draw, and remaining runtime. Ollama is running completely locally. We have two local AI models that we have completely offline. No API key, no cloud, nothing like that. And then if we come down here to the data fetchers, these are the system MD timers that wake up on a schedule and pull data from Las Vegas Metro Police Department crime incidents hourly, weather every 5 minutes, news feeds every 15 minutes, points of interest weekly. And you'll notice that the internet feeds these, not the access point. So the access point works regardless of whether or not you have internet. And then obviously we have the storage through the solid state drive and the SanDisk. That's going to have all of that stuff stored locally as well, and then also fed into this Node-RED. Now here's a system that brings all of these capabilities together, Node-RED. Every single one of these services, dump 1090, the Mesh-tastic bridge, the radio supervisor, SIGINT, the battery monitor, Ollama, all the fetchers, none of them talk to the dashboard directly. They all feed through Node-RED. Node-RED is the integration middleware. Think of it as a switchboard. It's about 200 nodes across 12 flow tabs, and its entire job is reading from all these services, normalizing the data, and exposing it through a clean set of API endpoints, such as all of these. It also reads from storage, and it takes things like the PMT map tiles, the dashboard HTML and JavaScript, the cache, crime, and weather data, the Mesh-tastic state files. When you load a map, you're getting vector tile data from a 1.95 gigabyte file sitting on the NVMe drive. No internet tile server, no CDN. Node-RED serves it with HTTP 206 range requests. It reads only the exact bytes needed for whatever zoom level you're at and location you're looking at. Now we will take a look at the dashboard. The Tactical Dashboard is a browser application. It runs in Chromium on the built-in display, but it is not a Pi process. It is a web page. Any device connected to the hotspot can pull it up. Your phone, laptop, tablet, anything can type in the same URL and they'll get the same interface. The dashboard pulls Node-RED's API endpoints, uses server-sent events for real-time updates like incoming mesh messages and SIGINT detections, and pulls audio from the radio stream directly on port 8090. So the key principle here is that nothing bypasses Node-RED to talk to the dashboard. Every data source has one path in. That's what makes it reliable, and it what makes it easy to add new capabilities without breaking everything that already works on this system. Alright, now we'll take a look at the dashboard. I'm going to go through every tab and tell you exactly what you're seeing and what's running in the background to make it happen. The dashboard is the primary interface. It's what the whole system is built around. The top bar is worth looking at before we get into the tabs. The MGRS coordinates in the center show my GPS position, not my actual one. I think it's showing somewhere in the middle of downtown Las Vegas right now. But that's military grid reference system, standard 10-digit format used operationally. The green dot means GPS is locked to a real satellite. Gray dot means it's showing map center. The clock is always in Zulu UTC. Every timestamp throughout this dashboard is going to be in UTC. And going down to the map engine is Map Libre GLGS version 5.7 with a ProtoMaps PMT tiles base map. PMT tiles are a single file archive format for vector files instead of a tile server that the browser reads only the byte range that it needs from a local file. For example, the Las Vegas metro is 40 megabytes, the US Southwest region, Nevada, Arizona, New Mexico, Texas, Oklahoma, Arkansas, and Louisiana are 1.95 gigabytes at zoom level 15. Both are on the NVMe drive. The map has never made an external network request. All layers default to off. The map loads immediately with just the base map. You activate what you need. This is intentional. Loading 35 megabytes of FEMA flood zone polygons in the background at startup would definitely freeze the browser for like 10 to 15 seconds every time. And then if we pull up crime data, you'll see 131,000 Las Vegas Metro PD crime incidents over the last 365 days that are rendered as a heat map. Calls for service filtered down to shootings, robberies, weapons incidents as individual colored dots. The fetcher runs hourly and uses incremental delta updates keyed on database object IDs. So the refresh takes about 8 seconds instead of 4+ minutes for a full re-download. And then if we pull up the POI layer, there are 12 categories for points of interest from OpenStreetMaps via Overpass API, hospitals, fire stations, police stations, cell towers, power infrastructure, military installations, fuel stations, critical bridges, water treatment, railroad, airport, and FEMA flood zones. Each is a separate layer that you can toggle on independently. The map settings panel is on the right and handles all of this. If we pull up the ADS-B tab, we'll see the aircraft appearing on the map here. It's going to show us call sign, heading, altitude, and speed. As you can see on the map, there's only 2 aircraft, and there's probably a lot more in the Las Vegas area. I'm employing this box indoors, so that's limiting the reach of my ADS-B antenna. But all of this information is repeated over on the ADS-B tab, and we have historical data on the right, as well as the current data on the left, showing a different format, a little bit easier to read. And if we click that Meshtastic tab, it's going to pull up all the Meshtastic nodes in our area, and it would also show my current GPS position if that setting was currently enabled, but it's not right now. We also have the MGRS coordinate search bar. This accepts MGRS, decimal degrees, and decimal minute seconds. As you move across the map, the cursor readout in the lower left shows both MGRS and lat long in real time. The left toolbar has an annotation tool as well. You can do points, lines, polygons, circles, freehand. Everything you draw saves to GeoJSON file that is survives a reboot every time. The range ring tools and bearing distance measurements are also in there. Both display results in MGRS. Moving on to the OSINT tab, this is an aggregated intelligence feed. It includes news from 4 Las Vegas sources every 15 minutes. The Las Vegas Review Journal, the Las Vegas Sun, KLS 8, and WS alerts for Clark County. It also displays Las Vegas Metro PD calls for service every hour. Additionally, Meshtastic messages from the mesh, scanner events, and SIGINT proximity detections will be shown on this feed as well. Everything shows in reverse chronological order and is Zulu time-stamped. The summarize button at the top of the feed sends the last hour of intelligence items to the local AI and asks for a tactical briefing. The response streams token by token in real time on the screen. It's all completely offline, no API calling going out. So full disclosure on the AI summary and how long it actually takes. I did have to cut this video just for time's sake. It took between 7 and 10 minutes to fully render that OSINT summary. And this is because of the Quinn models that I'm running, 1.5 and 3. And if you look at the chart here, it'll show the actual parameters for those models. And then this next chart, I don't even believe that 1.5 and 3 show up on here, but they would be below Llama 3 or QuinQ, Anthropic Claude 3. It's going to be below all of those, and then you can see most of the mainstream AI up here with Google Gemini, Anthropic's Claude 3.5 Sonnet, and OpenAI's latest model. So it is limited by what the Pi is actually able to run. It's not super useful, but it at least is a cool feature to have on this device. For the Weather tab, weather is pulled from the National Weather Service public API, no keys required. Current conditions are from KLAS Las Vegas Airport, with 2 backup stations if KLAS is unavailable. We've already covered the ADS-B tab, so I'll move on to the radio tab. Full disclosure, this is one of the few features on this build that I have not managed to get functional yet. In theory, this will have 62 preset frequencies across 11 categories: NOAA Weather Radio, Las Vegas Aviation including Tower, Approach, and Guard, Amateur Radio Repeaters, FRS, GMRS, MURS, and Las Vegas Metro PD, Marine Business, UHF, and Broadcast FM. The power button at the top right starts the radio service supervisor service, and audio streams to the browser as Opus WebM. Once again, this feature is not functional yet, and I believe it's an issue with the FM AM demodulator and turning those signals into audio, because right now all I'm getting is beeps across all the different channels. I've been trying a couple different things to resolve this, and it's at the top of my list to fix before moving on to any upgrades on this build. Now on to a service that actually works. The Mesh tab is the Meshtastic command console. There are 3 columns. Left is the channel list with unread badges. You can have multiple Meshtastic channels active simultaneously. Center is the node roster with real telemetry for every node that the radio has heard. In the Las Vegas Valley, I'm passively receiving 149 known nodes. That's just between the mesh density here, solar-powered fixed relays up on the ridgeline, mobile nodes, and everything between. The chat is stylized like Merc chat for anyone that's in the military that is familiar with that user interface. Monospace JetBrains mono font, Zulu timestamps in the square brackets. Each call sign gets a deterministic color based on a hash of the call sign string. So alpha-1 is always the same color across every session on every device. System events for nodes joining and leaving appear inline. To direct message a specific node, type \message and then their call sign. The SIGINT tab is a passive 802.11 signals intelligence function. What's being captured are probe requests. Management frames that every Wi-Fi enabled device broadcasts when it's scanning for networks. When monitor mode activates, the alpha adapter stops being an access point for other devices and starts capturing raw 802.11 frames. The system hops across 18 channels, 2.4 and 5 gigahertz interleaved, at 2 seconds per channel, completing a full sweep every 36 seconds. In theory, I could install another Wi-Fi dongle to accomplish this task, but I just decided not to for now and have it switch between hotspot and scanner. Each captured probe request is an OUI resolved against the Wireshark manufactured database, 57,000 entries and classified. Known means the MAC is my own device whitelist. Randomized means the device is using a privacy MAC with the locally administered bit set. This is the default on most modern iOS and Android devices. Unknown means an unrecognized or non-randomized MAC. Those triggers a ticker alert. The RSSI spark line is a 60 sample history of signal strength. A rising line means the device is getting closer. Patterns of life detection flags any device that appears in 3 or more separate monitoring sessions or more than one location. The 30-minute auto revert timer restores the hotspot automatically if you walk away and just forget that you have the SIGINT tab active. So the whitelist is really where you get the most bang for your buck. You can whitelist your device, and any device that comes in with a randomized MAC or something crazy, then you could get an alert for that. This is a design that I intend on improving on in the future, but this is the baseline for it. For the media tab, this is a file browser of the 1 terabyte external drive. All standard media types play natively in the browser. The primary use case here is the KWIX offline reference library. Full English Wikipedia, no images, about 70 gigabytes. Every U.S. Army field manual and technical publication, medical reference via WebMD. which is a healthcare focus and written for practitioners, Wikibooks for technical reference, and Wikivoyage for geographic context. I plan on expanding on all these in the future, but for now, this is what I have available on that SanDisk. So we covered the AI pretty well when I talked to you about the OSINT tab. We've got that 1.5 and 3 Quinn model 2.5 running. It is good for what it is. You're on an 8 gigabyte Pi, so you can't expect it to be like Grok or Gemini or ChatGPT, anything like that. But if you want to ask it some general questions, I know in the past I've asked it convert gallons to pounds and things like that, and it did relatively well. But it's a $75 computer with no cloud connection, so it's not going to blow it out of the water. In the future, I don't know in this exact setup how I could upgrade it. Put a graphics card in the Doom box. I highly doubt I will do anything like that. This is a very tertiary function, so I'm happy with it as is. I don't really expect huge performance out of these models. And lastly, we have the System tab. The System Health tab has 7 monitoring cards. Battery shows the pack percentage, individual cell voltages from the SW2106 fuel gauge, charge state, current draw, and runtime. CPU shows per core utilization bars and temperature sparkline. Memory, and that's a disk for both of the drives. Network throughout the interface. All 18 services with uptime and connected devices. So that is what I have so far, but where am I going to go from here? Over the next 6 months, I have a pretty clear roadmap of where I want to take this build. I'm going to start with the cleaning up the UI and going global with the maps. Right now, the offline maps cover the US Southwest. The goal is a tiered system, a whole world base map, always on the drive, deeper regional coverage you can download before you deploy, and satellite imagery pulled on demand when internet is available. The dashboard itself is getting rebuilt with a proper component architecture, customizable layout, and sidebar navigation that actually makes sense on a touchscreen with gloves on. And after that, I'm going to look at the intelligence capabilities of this device. The OSINT feed right now pulls from Las Vegas local sources. The plan is to expand that to 50 plus feeds globally, conflict tracking across the world, disaster alerts, and disease outbreaks monitoring from ProMed, space weather from the NOAA, all geolocated and plotted on the map. I'm looking at a full Meshtastic feature parity with the official app, Spectrum waterfall display on the radio tab, signal recording with the squelch breaks, and probably my favorite feature on this list, a mumble voice client built directly into the dashboard, push to talk without opening a completely separate app. Forward, we will take this display into an analytical platform, aircraft history databases, flight path replay, Bluetooth passive scanning alongside the Wi-Fi SIGINT, geofence alerts for device correlation across sessions, and then we'll move into offline knowledge base. I want a full, even more full Wikipedia, more military field manuals, more medical references, a stack overlay offline dump, all searchable through a single bar for every installed library simultaneously. More of the hardware side of it, looking at an emergency white button, a VPN kill switch, screen lock, and automation engine that lets you define trigger and action rules. If battery drops below 20%, throttle the AI, things like that. If a military aircraft enters within 50 nautical miles, push an alert to the mesh. If it's 0600 Zulu, generate a broadcast for the morning sit rep automatically. So it'll automatically push me that morning sit rep first thing in the morning. But the whole roadmap is a little loose right now, but I do plan on expanding this in the future, and I'm looking forward to any input from people that know more about any of these systems than me. I'm very new to all of this, so I'm always open to input. And thank you all for your time, and I hope you enjoyed this or got some ideas for your own build. But you all have a great day.